Yeah, off we go. So here's where we left off last time. We were talking about higher order partials. And reminder, the big idea of higher order partials is that if you take a partial, whatever you get, you can take a partial of that, right? And we talked about the algebra, we talked about the notation, we talked about this cool fact that the coincidence that we observe is not a coincidence and is true in a very broad category of cases, which is pretty nice. Something to be aware of. And now on to one of the bigger questions, and somebody already asked this, but what does this look like, right? Very reasonable question. Whenever you define a construction of any sort, you should always kind of have this urge to want to have some way to visualize it or at least relate it to things that you can visualize, something along those lines. Okay, all right, so these unmixed partials. It turns out there's a really crisp answer to how to visualize this, and it's familiar even, and it's familiar for what I'm going to call pretty obvious reasons. So let's start with FYY, just because it's a little bit easier to draw the picture of. How would I compute FYY? Well, let's see, to take the first y partial, I have to hold x constant. Holding x constant, of course, means that we're going to fix a value of x and look only at that value of x. Namely, we'll be looking just at that cross-section, which is sort of the top of that Pringle I have drawn there. And then take the derivative with respect to y. And then I'm going to hold x constant again. Okay, I already had it constant, so that's not even news. I'm just taking the derivative with respect to y again. We're literally, after holding x constant, we're just taking literally the second derivative with respect to y, and we already know the interpretation of that, right? The interpretation of second derivative with respect to y is concavity. And of course, concavity of this cross-section, so said differently, it's concavity in the y direction. So FYY, because this is concave up, positive. Does that make sense to everybody? Okay. Likewise, if you want to talk about FXX, picture's a little bit different, right? Y is being held constant, so we'll be looking at a cross-section like so, which is like that, which is concave down, and thus negative. Okay. All right, so that's pretty quick. Where things, and more to the point, familiar. We're basically piggybacking off of an old idea from single variable calculus. Okay. Not so with this next one. This is a trickier one. And we're going to use ideas we've already talked about, and in fact, the ideas we're going to use here could be taken as sort of a point of view on why that whole concavity thing came up in the first place. But we're going to be applying it to a different situation, and the answer is not going to be concavity. The answer is going to be unfamiliar, because there is no single variable version of a mixed second partial. You can't have single variable mixed second partials or second derivatives of any sort, because there is only one input variable to take derivatives of, with respect to anyway. So we are in uncharted territory here. Of course, I can view this, to be more precise, as this. To say that differently, this is the y partial, and then we're going to take the x partial of that y partial. Now let's ask geometrically, what does that look like? The first part of that, what does the y partial of f look like, is easy. The y partial of f says, okay, from wherever I might happen to be, I'm going to go in the y direction. I'm going to look at the tangent line to the graph. Tangent line to the graph, which let's say would be a line kind of like that. And by the way, just for sort of geometric I'm trying to draw that, that's direct. That's its shadow is that horizontal line, green line in the y direction. And so this y partial of the slope of that tangent line to the graph in this direction. And you're going to notice in the picture I didn't draw the graph. When I first tried to draw this picture, I tried to draw the graph. some graph that had sort of geometric features that I needed to have in order to be able to do what I need to do here. And frankly, it just makes the picture more cluttered. Okay, so I'm going to ask you to use your imagination, right? Imagine that there is some surface. And of course, when you have a surface and you talk about a certain direction, you can talk about the corresponding tangent line. So I'm just not going to draw the graph, but imagine it's there. And that's what we're taking the tangent of. Okay. So we get something like that. Fine, no problem. How about we do the same thing? Oh, by the way, that's the interpretation we're making of that y partial. So why don't we do the same thing for taking the x partial? Well, can't I just say the x partial is the slope of the graph in the x direction? And there's a frustratingly persuasive answer to that question, and that is because I'm not taking the x partial of f. I'm taking the x partial of this other thing. I'm taking the x partial of the y partial of f. I'm not looking at a graph of the y partial of f. I'm looking at a graph of f. So I cannot view this x partial from the point of view of, well, it's the slope of the tangent line. It isn't. I'm looking at the wrong graph. So I have to think of some other way to interpret the x partial. How else might I think of the x partial? And remember, we have this other interpretation that says, look, it means you're moving in that direction, and you want to know how fast is that thing that I'm taking the x partial of changing. Right? So that's the interpretation we're going to make. I'm going to say, look, as I move in the x direction, I want to know how fast do these y partials, like so, how fast do those slopes change as I move in the x direction? And so that's why I drew several of these y slopes. Now again, there is no graph for you to refer to here. Use your imagination. But let's just say that the graph has the feature that, back here, the slope of the tangent line in the y direction is like so. And then as you move forward, as you move in the x direction, like I've got in blue, that those tangent lines kind of progress like I have drawn here. Now let's sort of just directly consider, as I move in the x direction, how fast of a change are we seeing of those slopes in the y direction? Okay, well, this one looks to be about -2. This one looks to be about -1. This one looks to be, I don't know, like -0.5. This one looks to be about 0. This one looks to be about +0.5. These y slopes, as I move in the x direction, seem to be consistently increasing. So the rate of change in the x direction, because the things that we're taking that rate of change of are consistently increasing, that rate of change in the x direction is positive. So something whatever it is about the shape, whatever that shape is, something is making that rate of change positive. And I tell you what I think it is. Now I'm going to take a stab at trying to draw the graph of the underlying surface, and you can see it's kind of like that there, but then it's kind of twisted, if you will, and this is very difficult to draw. So the best way that I have to visualize what this surface actually looks like because of these tangent lines behaving as we just described is a literal hand wave. So it's like this. Let me not block my own. It's like this back here, and then as I come out of the screen, those slopes are doing this move. Y'all see what I'm talking about? And how would we describe that? Geometrically, how would I describe that? I call it a twisting. Right? It's like, imagine I had a sheet of rubber. I don't know how to get such a sheet of rubber. Imagine I'm holding the sheet of rubber by the four corners, like this. I've literally twisted the surface. It's a hard thing to visualize, to be fair. But anyway, this is the geometric interpretation. The term is torsion. Unfortunately, that term gets used for other things as well, so whatever. But anyway, geometrically, it's like the graph has sort of a twist in it of sorts. So again, unfamiliar, right? This is not oh yeah, that's just like back in Calc 1. No, there was no version of this in Calc 1. Uncharted territory. And that's what we got. Okay. Yeah, it's a good little brain bender. It's a good idea to spend some time kind of getting used to this. And, yeah. Right, yes?
Is it like imagine like there is a mountain range and the x, the d over dx here is like you go to one direction, let's say east, and you go east, and then the slope of the mountain kind of change.
Yeah. That's right. The slope. Yeah. Imagine. Yeah. Okay. Sure. Let's play with that metaphor. Imagine I'm standing here and I'm on the side of the hill, and it's uphill that way and downhill that way, right? And I'm going to go in a straight line, and I'm going to use my hands to describe what the slope is in that direction. And it's like as I walk, the slope is doing like this. Now downhill's to my left. Downhill had been to my right, but because of this twist, now downhill's to the left. Yeah. So that'd be a weird trail to hike on, but that happens. That's a thing, right? Yeah. Okay. Alrighty. So here's where we do a little bit of a jump. There is more Chapter 2 to be done, but the way I like to do that remainder of Chapter 2 stuff is using an interpretation that we're gonna talk about now. And if we have to jump up to Chapter 3 real quick, cover this. That gives me an interpretation I want to use, and then we're going to go back into Chapter 2 momentarily. Okay. All right. So here it is. Flashback. Don't forget about parametric curves. Right. Remember, a parametric curve. The big idea is that we have. Whoops. What's going on here? This died already? What is up with that? That is so weird. I just unplugged it. All right, that's working. Okay, so, oh gosh. I can't read that. Okay, there we go. Okay, so remember the idea of a parametric curve is we have position in space, so the value of a parameterization is position, and it's as a function of a single parameter, and of course we usually view that single parameter as time. Right, so position as a function of time. Okay, that said, let's talk about the derivative matrix of such a thing, and here it is. Now the observant among you will notice a problem. Hey, wait a minute. I thought D matrices were supposed to be made up of partial derivatives. How come I'm allowed to call these regular? I use D instead of partial, right? That's you're not supposed to do that. Why is that okay here? The reason why is, let's think about how you take partial derivatives. And the process of partial derivatives is you hold all the other variables constant. Okay, wait a minute. Whoa, slow down. We're taking a partial with respect to T. T is the only variable. There are no other variables to hold constant. In this case, the partial derivative is literally the single variable derivative. So when you have a single variable vector valued function, namely a parameterization, the derivative matrix is the column of single variable derivatives of the output coordinates. So, nice little fact to keep in mind, and that's gonna show up in a couple other places today. So anyway, there's that. Now, let me remind you of we have this old single variable definition of a derivative of a function, and we should be a little hesitant with this. We should be a little concerned. Hey, wait a minute. When we wrote down this definition back in Calc 1, we had single variable functions in mind. Does this actually make any sense in this multivariable context? Are we going to have a consistency problem? Are these going to end up being related somehow? Fingers crossed. Oh my gosh, they better be. Right. Does it mean something geometrically in a natural way? There are many concerns about writing this down. And here's the good news. Yeah, it's all good. The reason why is, well, two reasons, I suppose. First of all, I claim these are actually equal. And you can see this as follows. Look at the definition that we have here on the right. We've got a limit of a fraction involving a difference. And let's just think about how do we compute these, every aspect of what we have on the right. How do I take a difference of two vectors? Well, one coordinate at a time. How do I multiply or divide by a scalar? One coordinate at a time. How do I take a limit? You kind of skipped over that part, but I hope it is not surprising if I say you take limits one coordinate at a time. This whole computation, namely what I would like to call the single variable derivative of this parameterization, it's done one coordinate at a time, which is what this says. That's exactly what the derivative matrix is. So concerns and ultimately concerns that are completely resolved. Okay. All right, so that in mind, let's try to figure out what this means geometrically. And this is kind of a straightforward part. I mean, if you look at what we have, that is literally a displacement between 2 points on the parametric curve, right? Where there's a question of where you are at time t, and then there's a question, where are you at time t plus h? That literally just says, okay, what was your displacement between those 2 points? That's what a difference vector is. And so displacement per unit time, because h is literally, right, this denominator that I have is literally the elapsed time between those two moments. So this is displacement per unit time, and y'all will recall that displacement per unit time is velocity. So old news. By the way, very familiar, I hope, again from Calc 1. Right, one of the first things you do with derivatives early on in a single variable calculus course is observe that if the function gives you position, then the derivative gives you velocity. The only thing that's really different here is that now position is has multiple variables. Position is 2 or 3 dimensional, and so the velocity is correspondingly 2 or 3 dimensional, multi-dimensional, whatever the appropriate dimension is. And therefore is a vector instead of a number. Everything else is pretty much the same. Okay. Alrighty. So with that in mind, likewise, not only is velocity the derivative of position, but acceleration, I was on the race mode. Acceleration is the derivative of velocity, and therefore the second derivative of position. Okay, so again, familiar from way back when. Okay, so a very plug-and-chug computational example. Y'all have done single variable versions of this many times. I expect this to be mostly a yawn. I'm going to go through it quickly. Y'all should and can check the details, right, at some later time. But in this question, we're given velocity, and the question is to determine acceleration and position from the given velocity. And by the way, we're also given an initial position, as we will need in a second. So, unsurprisingly, as we just discussed, acceleration will be the derivative of velocity, and position is the antiderivative of velocity. And, y'all know how to do those, right? You take as we just discussed, you take the derivative one coordinate at a time. Likewise, you take the antiderivative one coordinate at a time. Good opportunity for me to remind y'all, I do assume that y'all are proficient with derivatives and antiderivatives and all those various rules, integration by parts, substitutions and stuff like that, right? So if you're maybe a little rusty on some of that stuff, this is the time to polish up those skills. That stuff never goes away. So make sure you're good with that stuff. Okay, now here's the tricky part. When you're doing the antiderivative, of course, you do have to be careful. Don't forget your plus c. C, of course, now is a vector. And what is the value of that C? We are going to do this in the usual way. I'm going to look at this equation, and I'm going to plug in t equals 0 into that equation and see what happens. And, well, the position is 5, 6. That's given. And let's see here, algebra, mere algebra, not even algebra, just arithmetic. I plug in t equals 0 into this expression. I get 3, 1. And, of course, the C comes along for the ride. Right? And so that dark blue equation becomes this dark blue equation just by plugging in t equals 0. Is that cool? Everybody happy? Okay. And then, no problem to solve for C. You can straight up just solve for C, and here it is. Okay, so nothing to it, easy to do. Here's what trips up a lot of students. A lot of students have this delusion. I blame high schools sympathetically, but nevertheless, high schools very often are the culprits in causing students to believe that, hey, wait a minute, shouldn't this equal to that? How come those aren't equal? And in fact, I have been there myself. Believe it or not, there was a time when I was in high school, and when I was in high school, pretty much every example I ever saw, the integration constant ended up being the same as the initial value, the initial condition that I was given. So, how come it didn't work here? Well, I'll tell you where that mystery comes from. It's not hard to track it down. If you sort of expect that this should equal to this, right? If that is your expectation, that the integration constant should be your initial value, what you're saying is that you're kind of expecting that this should always be 0. And the thing is, this came from that. Why would it be that when you plug t equals 0 into an expression like this, why would you just expect it to be 0? The answer is because very often high schools only put polynomial type questions, right? And if this is a polynomial, take it to the bank, guaranteed. You know for sure that every function that will ever be given in this form is a polynomial. The antiderivatives that you'll write down will be polynomials that all have factors of t, and then you plug in t equals 0, and every time in that narrow, limited, unrepresentative collection of cases, it'll always be 0, and that creates this illusion that these should be the same. And it is a artifact of this arbitrary nonsense of, we're only going to use polynomials, right? So that's not how the world works. This is a pretty broad misunderstanding a lot of students come into this class with, and make sure that that's not you, right? So now in terms of how this affects y'all, right, there's a couple of ways that this will affect y'all. First of all, you want to be able to get right answers. That's clear, right? Okay. Worse than the fact that misunderstanding this point will give you wrong answers, much worse than that, is it will cause you to make invalid reasoning. And don't forget, that's what this course is about, right? Deep down, fundamental philosophy of the course. This is a course about reasoning and ideas. This is not about facts and answers and, stuff like that, right? So the fact that it gives you the wrong answer is superficially a problem. The fact that it is invalid reasoning is the real problem. So, with that in mind, I'm not saying I won't ever give you one where it's polynomials, right? If it should be the case that I give you one where this is a polynomial, And if what you write down as your integration constant is therefore coincidentally correct, but you don't have a valid justification for it, the justification is what we're looking for. The reasoning is the point. That's what this course is about. And so again, it's the fact that you would get the right numerical answer, lucky coincidence. That's not how the course works, and that's not where points come from. And an unjustified, coincidentally correct numerical answer doesn't get credit. I hope that makes sense to everybody. I mean, again, this is an important part of the deep down the philosophy of the course. And I just want to make sure that everybody has a crisp understanding. I don't want this to surprise anybody on an exam. Okay. All right. Enough of that. Okay. So real quick, there is a bunch of stuff, and by the way, this is noted on the content syllabus. There's a bunch of stuff about Kepler's work on planetary motion, and it's very cool. It's historically cool, right? Neato stuff. But this course is packed, and we have too much material as it is. And this, however cool Kepler's work is, isn't really in the sort of the prerequisite trail of the critical material that we're working to get toward, which is the chapter 6 and 7 vector calculus material. And so, sad though it is, we are skipping that Kepler material. You're not responsible for it. But, again, as I wrote here, which also is clarified on the content syllabus, you are responsible for proposition 1.4. It's just a pretty convenient little, it's no big deal. It's basically just observing that we have a couple of product rules that are exactly what you would expect and hope them to be, right? So it's not, this is not a big ask, right? But we are going to use this in a few places throughout the rest of the course. So that part you are responsible for. All the rest of the Kepler stuff you can skip. Okay, moving along. So back into chapter 2. Quick jaunt to early chapter 3, back into chapter 2. Chain rule. Y'all remember the single variable chain rule. The multivariable chain rule is very analogous. But the context is so different, it brings up a lot of related questions that are going to be pretty unfamiliar. So deep down, very analogous, but in practice, pretty different. So anyway, here we go. This first page I have is really just a kind of a refresher, reminder of single variable, and I know y'all are good at single variable. My point to this first page is not to brush up your single variable chain rule understanding. My point here is to establish a very particular and carefully chosen point of view on the single variable chain rule. And there are many points of view on the single variable chain rule, all good, all fine, no problem, right? But I want to take this one, because this one is the one that's going to extend naturally to multivariable. And by the way, you're going to find that that's the case with a lot of stuff I do in this course. We're going to choose a very narrow, particular point of view on some single variable concept because it extends so nicely and naturally to multivariable. All right, so the point of view I want to take here is, let me remind you that when you have a single variable function, you can talk about input velocities and output velocities, and you can talk about derivatives. You can talk about derivatives as sort of what you do to input velocities to get output velocities. Now, this is just a point of view, but that input velocity, we multiply by the derivative to get that output velocity. Lots of other points of view on single variable derivatives, all fine, but not what we want here. Here, very narrowly and particularly and importantly, we're going to view derivatives as multiplicative factors. Derivative is a factor. Forget about slopes. Forget about velocities. Here, momentarily, derivatives are multiplicative factors. Is that cool? Is everybody on board with that? Okay, so we gotta get onto this page, and with that in mind, now let's look at a composition of functions and take again exactly this point of view. If I have a composition of functions, well, then velocity of x will cause a velocity of y, which is the input to this next function, which will therefore cause a velocity of z. Right? Now I've got three velocities, and let me remind you that, and let's see here, let me highlight appropriately. Give me a second to just get everything highlighted. So with that noted, don't forget, the derivative of f is this multiplicative factor. It's what you multiply by green to get blue. It's a multiplicative factor that you take at that stage. What's the derivative of g? Well, the derivative of g, again, it's a multiplicative factor. It's what you multiply by there to get there. And what is the derivative of the composition? Well, the derivative of the composition is what you multiply by that to get that. So, I've got three velocities, x prime, y prime, z prime. But I also have three factors. I've got the derivative of f, the derivative of g, and the derivative of the composition. Now I'm going to make what I consider a very modest suggestion, which is that if you were to take whatever value, I don't care, any value, if you multiply by 3, and if then after that you then multiply by 5, altogether you've multiplied by 3 times 5. Right? No big deal. Of course you have. So with that in mind then, multiplication, this purple multiplication and this dark blue multiplication, successively multiplying by 2 factors, well, altogether you've multiplied by the product of those factors. And so now let me erase the stuff that we no longer really need. I don't really need this stuff anymore. I just look at that. Whoops. And if I can get this to cooperate, there we go. Altogether, the overall factor is the product of the first factor and the second factor. And there's your single variable chain rule. Very familiar, right? Y'all have seen this a million times. That's a point of view on it. A succession of factors is a product factor. That's all it is. Okay. All right. Now, why did I spend all this time on single variable chain rule? By the way, if you want to write it down in terms of algebra, you'll notice I have various equations, and I've talked about how you can plug this into that and blah, blah, blah. That's just algebra that documents what I think is better understood with this intuition. So with this intuition in mind, now let's look at the multivariable take on this, the multivariable version. And it's the same thing. Oh my gosh, so the same thing. We have, again, a particular point of view on derivatives. Namely, if I have an input velocity and an output velocity, then I relate those two velocities by multiplication by the derivative. That's what derivatives do. Derivatives turn input velocities into output velocities. Yeah, there's other takes, there's other points of view, blah, blah, blah. But this is the narrow, special, particular point of view we want here. Derivative matrices are factors. It's what you multiply by one vector to get the other vector. And real quick, let's just observe. Thinking of the derivative as a multiplicative factor, that's exactly what we did here. We thought of the derivative as a multiplicative factor. Yeah, that one's a scalar. Yeah, this one's a matrix. Granted. But still, multiplicative factor. And so the same argument extends when you look at the composition. If you've got an input velocity, which causes y to have a velocity, which causes z to have a velocity, and if you think in terms of, okay, well, what do the various derivatives do? Well, I want to get my colors straight here. Purple, blue, red. Okay, so the derivative of f is this multiplicative factor. The derivative of g, where did I put it? Here it is. The derivative of g is this multiplicative factor, and the derivative of the composition is the overall combined multiplicative factor. And again, when you multiply by something and then you multiply by something else, multiplied by the product. Again, that's a modest suggestion, right? But if you multiply by something and then you multiply by something else, you altogether multiply by the product of those two things. And so just like we reasoned previously, that composition factor, the derivative of the composition, is the product of the first factor, aka the first derivative matrix, and the second factor, aka the second derivative matrix. And this is a powerful conclusion. Oh my gosh, this is arguably very unexpected if you look at what this is saying, right? This is saying that derivative matrices that we wrote down as a notational shorthand, right? So we don't have to write out a bunch of terms, dot, right? It's just a shorthand convenience. Wow, they multiply when you compose functions, and it follows immediately just from interpreting derivatives as multiplicative factors for velocity factors. This is a big conclusion. And by the way, it becomes really hard to figure when you sort of think about these derivative matrices, in terms of their elements. If you think in terms of partial derivatives, and we will do that in just a minute here, but it's a lot less. It requires a lot more sort of, I really got to think this through. Much less obvious. And much more of a surprising result. Oh my gosh, look at this. They actually combine. Matrix multiplication is exactly the thing that you're doing when you take a derivative of composition. Oh my God, it's much more surprising. I think that from this point of view, it's, I don't want to say obvious. That's a kind of a bad word in a sense, but it's pretty immediate. I mean, this is just a factor, and the overall factor is the product of the individual successive factors. Is a modest suggestion, right? So the following happens a lot in math, and that is when you view things from the point of view of sophisticated tools, sometimes seemingly hard problems turn into easy problems. Very important thing in math, right? And that's why mathematicians like sophisticated tools. In short, is because they turn hard problems into easy problems. Okay, all right, enough of that. Okay, now let's see here. I do want to point out there's a really nice way to think about this, and that is what I have highlighted here. Differentiation turns compositions into products, and here it is. Literally a composition of functions, and when you take the derivative matrix, you get a product, matrix product of the individual derivatives. So I think it's a really nice, pithy little way to think about the chain rule, the multivariable chain, the matrix form of the multivariable chain rule. Wow, what a mouthful. Differentiation turns compositions into products. That's kind of all it is. All right. One other thing I have to talk about, and this is a subtlety, an easily missed subtlety. Let's talk about where to evaluate these various different matrices. And in particular, this matrix here, you'll note I have evaluated at the point A, namely here. Why did I evaluate that matrix at that point A? And well, because that's where I was when I did this, right? That's me right there where the A is. That's where I am when I say, hey, if I start moving with velocity x prime, how fast does the output move? So you evaluated A because that's where you're taking action. That's where this matrix acts. Okay, likewise, why does the composition get evaluated at the point A? Well, again, because that's where I am when I do that, right? What the derivative of the composition does, it turns x prime into z prime, and I'm at the point A when I'm doing that. Okay. All right, and where things get a little different is when you think about why is it that dg is not evaluated at A? Why is dg not evaluated at A? Well, because I'm not at A when I do what dg does. That's what dg does. dg turns this vector into that vector, and that happens when I'm here. At this point f of A, that's where I am when I say, hey, well, if I'm moving with velocity y prime, how fast is the resulting, right? I'm at the point f of A. By the way, the function g has never heard of this point A. G has no idea what A is way over there. It's not even in the domain of G. If I were to say, evaluate dg at the point A, that wouldn't even make any sense. Is that cool? Right. So this used to throw me for a loop when I was young. And I was like, my point of view on this, of course I was young, was, okay, A, that makes sense. A, that makes sense. Hey, what? Why f of A there? What? That seems inconsistent, seemingly. It's perfectly consistent if you look at it the right way. Okay, how we doing? Everybody happy? Let me see if my good stylus is working again. We're back in business. Okay, let me put this one back in here. Okay, so let's see an example. Oh, you know what? I got ahead of myself one other time. This works for any combination of dimensions. Up here in this picture, I drew 2 dimensions to 2 dimensions to 2 dimensions. I just needed to have some picture to be able to work with, right? So, the resulting matrices here, these are all 2 by 2 matrices because this is 2 dimensions and that's 2 dimensions and that's 2 dimensions. But it doesn't matter how many dimensions you have. All of this still works. And if you want to know what the argument would look like, if I were to, for example, what if this was a 3-dimensional, what if there was an x3 there, right? And what if this was 3-dimensional? There was a z3 here. Okay, well, no worries. The picture is still exactly right. This df still is the matrix. You multiply by that to get that, and et cetera, et cetera. It all still works. The only difference is that now df, the thing that I multiply by a 3-dimensional input velocity vector to get a 2-dimensional output velocity vector now has, let's see here, I gotta multiply. It has 2 rows and 3 columns. So the matrices down here will, they'll have different shapes, but the multiplication will always dovetail perfectly. Everything fits, everything works, and it's fine. And the picture almost doesn't change at all. Okay. All right. So with all of that in mind, now let's see an example. Let's get our hands dirty here. Got a function, got another function, We're going to compose these functions. You can kind of tell we're going to compose them because the outputs from f are the same as the inputs to g. That's what it means to compose. Right? By the way, I do think it's a really good idea to, when you do one of these problems, always be very careful in your choices about what to call the various variables that play at various different stages, and make sure that the choices of variables that you make, is consistent with what you're talking about doing. Right? So if you're going to take the outputs from f and make them the inputs to g, make those the same names, because that's what you're doing. Okay. Now, weirdly, you'll notice I didn't give you formulas for f and g. So you can't explicitly compose and get a new grand total formula for the composition function because I didn't give you the formulas to be able to compose with. So we don't know what these functions' formulas are. We just know that they're functions and that we're composing them. And now suppose I further give you the following data. So I'm telling you the value of f at a particular single point. I'm telling you the df matrix at a particular single point, and I'm telling you the dg matrix at a particular single point. And with all of that given, the question is to compute the derivative of the composition and subsequently to compute that specific partial derivative. And notice this is a composition partial, right? We're taking the partial with respect to x1 of z3. So this is from one of the original inputs all the way to one of the eventual outputs. All right, so we're going to take this one step at a time. Let's start with the composition matrix. The very first thing I'm going to write down, I'm just going to write this down right there. We've already established this matrix form for the chain rule. So with that in mind, I immediately write down this. And I am happy about a couple of things already. The product that I want is the product that this seems to address, and that's great. And let's see here, wrong color. The DF matrix that I'm going to need is the DF matrix that I have. Isn't that awesome? And here's where I get a little uncomfortable. I need the DG matrix at f of 1, 2. Wait a minute. I have the DG matrix at 3, 1, 0. Right? We got to worry about this now. I can't just say, well, whatever, good enough. Right? We really, literally, we need DG evaluated at the correct point, f of 1, 2. And of course, the good news on this is that, it's the same. F of 1, 2 is 3, 1, 0. That's literally that. And so, colors. DG at 310 is what I have and also what I need. Everybody good so far? Okay. All right, so again, you got to be careful about this funny business, right? Make sure that you evaluate at the correct point because that's the requirement, as it must be. Okay, so now there is another little tricky bit to this, and I did this on purpose. Life will do this accidentally about half the time, but check it out. This matrix that I need on the left, in the list of facts I gave it to you on the right. Right? And this matrix that I need, colors. This matrix that I need on the right, I gave it to you on the left. Now that was, you could say, a dirty trick. Right? Students that are playing a little too fast and loose with the chain rule, just multiply the two matrices you're given. Right? Well, students that are too casual about this and not putting them in the correct order would have them backwards. Now, in this case, those students might have noticed, because check it out, if you were to have them in the wrong order, then the square peg round hole, you can't multiply the matrices, and that would probably give that student a heads up. Oh shoot, I should probably turn these the other way. Life will not always give you such heads ups, and it remains, life will about half the time, right? It's a coin flip. About half the time, the matrices will come to you in the wrong order. Right? So you got to make a conscious effort to think this through, and a couple different ways to think about this. Just keep in mind that the function that acts first, acting first when we draw diagrams means on the left, but acting first when we multiply with matrices is on the right. And that's just, there's this awkwardness about how, at least in U.S. math culture, how we, what order, we're left to right when we draw diagrams of functions, but we're kind of right to left when we compose functions, because that's sort of how this whole idea of how we denote functions, we put it on the left when it kind of should have been on the right. And this is deeply entrenched in U.S. math culture. We're not going to get rid of it. At least I don't see any way forward on that. I would love to get rid of it. I would love to change the convention, and consistent with with how we tend to write things down. Let's see here. Consistent. Well, let's see here. Where would I need some space to? Let me just give myself a little room here. Right. When we draw a diagram, and if I say X goes to Y, writing F of X, this notation already has it kind of backwards. The thing that was on the left is on the right, and the thing that was on the right is on the left. This is already a screw up. And really, honestly, it should have been written like that. Shouldn't have. Right? Now left is left, right is right, everything's the same, it's all consistent. Mwah. Perfect. Right? And apparently, I'm told, and I don't know this factually, but I am told that there are some hardhead, people out there that, with this exact point in mind, in fact, write functions like this. And I have never encountered this myself. But I got to hand it to them. I think deep down they are kind of right. But they're also inconsistent with the culture, and nobody does that. It's just, come on. It's just, you can't, it's too weird. Nobody else does this. Right? So, oh well. Anyway, the consequence is that, if you don't want to do it that way, then you have to accept that things are going to look backwards. And so you've been warned, right? Think it through. Be very careful. And in particular, as I was saying here, in the diagram is on the left, in the algebra is on the right, and notice further in the composition there is on the right. While what happens second, in the diagram is on the right, and the algebra is on the left, and in the composition also is on the left. Heads up, be careful, keep it straight, right? Don't step on this landmine. And yes, I know it's annoying, and I think the solution is worse than the affliction. Okay, so it's all over but the shouting at this point, right? We've got this product of matrices, fine. You know how to multiply matrices, boom. Everybody, we win. Let's see here. So this is that matrix that we wanted. Everybody happy? All right, now let's look at the second part of the question. I got to zoom here a little bit. Second part of the question. Okay, there we go. Second part of the question is to compute that specific second partial. That is one of the partials of the composition. Now, good news, I already have the derivative matrix of the composition. What is the derivative matrix of the composition? Well, it's made up of all the partials of the composition. What I've been asked for is one of the partials of the composition. So this thing I've been asked for is one of these numbers in here. I know it's one of these numbers. I just have to figure out which one it is. Right? So let's think through how would I identify which one it is. And there's a process for this. Very straightforward. Apparently I'm taking a partial with respect to x1. x1, you will notice, is the first of our input variables. Input variables tell you which column you're in. Right? And that's just one of the rules for how we write down derivative matrices. We're looking at a derivative matrix. Columns correspond to input variables. We want a partial with respect to the first input variable. That means we're in the first column. And then likewise for the output variables, right? So we're looking for the partial of Z3. There it is. Z3 is the third output variable. Okay? Output variables correspond to rows. So if we're looking for the partial of the third output, then we are interested in the element in the third row. And that means that we're looking for that number right there. And it's 3. Everybody good? All right, good deal. Okay, there's a couple of special cases there. I'm going to be real quick with these special cases. Again, y'all can read through the details, read the example. I think this is pretty straight read. But as usual, we hit some highlights. This first special case we're going to look at, suppose there is only one initial input variable. Right, we've got this matrix form of the chain rule. We can have any number of variables at any stage. We want to consider here the special case of when your initial space is one-dimensional. And I'm going to use t for that variable as well. Okay, so what happens? What happens to the chain? What's the chain rule look like in this case? Alrighty, well, modest observation. This first function now, check it out, its position is a function of time. It's literally a parametric curve in Rn. What's the derivative matrix of a parametric curve? And let me flash it back a couple of pages. Whoops. I better straighten this up. The derivative matrix of a parametric curve is a column of single variable derivatives that gives you the velocity of that parametric curve. Everybody remember that? It's from first thing it was early in what we did today. Okay. All right. So okay, cool. Back to where we were. So velocity vector. It's the velocity of the velocity in Rn. Okay, now let's think about what the composition looks like. The composition gives you, again, position. Now, y vector, right? Y1, Y2, Y3, whatever. Position in Rm as a function of time. Again, so we have another parametric curve, and its derivative matrix, again, is a column vector giving you the velocity of that parametric curve. Now, let me say that a little bit differently. This input velocity is a velocity in Rn. This output velocity is a velocity in Rm. And so what does df do? What's the conclusion that we're going to take away from this this special case of the chain rule? The takeaway is just a recovery of an old idea we already knew, and that is the chain rule seems to be telling us that the derivative matrix is what you multiply by an input velocity to get an output velocity. And again, we already knew that. Right? This is one of our interpretations that we made back in 2.4, I think. 2.3. Anyway, recently. Okay? One of our primary interpretations of the derivative matrix is it's what you multiply by input velocities to get output velocities. So now, not news. Why am I wasting your time with something that we already knew? I just think it's nice to observe that sometimes different points of view overlap, right? And so the idea that the derivative matrix turns input velocities into output velocities, we had a kind of a different take on that a couple of days ago. Here, we're viewing that same fact as being a special case of the chain rule. So, that's all. This example is, accordingly, all it does is the exact same thing that we just said, which, again, we knew a couple sections ago. This example could have been a couple of sections ago. I'm just putting it in here just to kind of show you how this really does look exactly like we already knew it would. And notice that what the question asks is it gives you an input velocity, and it asks you to compute an output velocity, and we do so by multiplying by the derivative matrix, which of course we got to take some partials and plug in the appropriate point, et cetera, et cetera. But all I'm doing is just, if you give me an input velocity and ask me for an output velocity, I multiply by the derivative matrix because that's what derivative matrices do. What do you think? Details to be checked, of course. Think through all the rest of the details. Make sure you can take these partials that I did right here. Again, that's for y'all. Y'all can read that, right? Make sure, though, that you're good to go with the partials and structuring the derivative matrix like this and not like that, right? There's various little devil details to think through and make sure you can do all that stuff. Okay, the next special case is, again, kind of old news. In fact, it's a special case of the special case we just looked at. We already talked about how if you have only one initial input, then this is the input velocity and this is the output velocity. Now we're going to add in, as a special case of that special case, what if you only have a single output, eventual output variable? Well, that just means that this matrix has a single row, and this is a single row in a single column, namely just a literal single variable derivative. And it's literally the derivative of that composition is a single variable function. One variable in, one variable out. So, why is this worth talking about? And depends on how you think about it. But because this is just an opportunity to point out that don't forget when you multiply by a single row matrix, that is the equivalent of dotting with the gradient vector. That's really the only thing I wanted to point out here. We've already made this observation, but I like to, remake observations in context sometimes. And a single row derivative matrix is the same as a dot with a gradient. Okay, that's all that is. And again, example, and again, pretty straight read. I'm going to let y'all read that one. I think it's very direct. It's just like the previous one, except using dot product with the gradient. That's all. Okay, give that a look. Okay, new point of view. So I spent a bunch of time talking about how awesome it is to use big, powerful tools, right? The derivative matrix turns out to be not only a convenient shorthand, but a powerful and natural, ultimately, simplification of how to think about multivariable derivatives. This is one object that turns the entire question of derivatives into, well, multiply by a factor. Which is pretty great. And then I talked about how, if you were to break this down into individual variables and individual partial derivatives, it turns into a nightmare, right? And it kind of does. And here's what that nightmare looks like. So keeping in mind that the way we take the derivative of a function like this is with the derivative matrix, and here's what those derivatives look like. And then the derivative of a function like that, well, again, derivative matrix, blah, blah, blah. And then if we talk about the composition that takes the x's all the way to the z's, well, its derivative matrix looks like this. And as we've already established, the derivative of a composition is the product of the individual derivative matrices. Again, powerful ideas gave us that conclusion. And now let's break this down into elements. Let's look at this one element of the product derivative matrix. How do we compute an element of a product matrix? Well, we do it with a dot product, basically, and it's the corresponding row of the left matrix dot the corresponding column of the right matrix. And notice, so when I say corresponding row, I mean the ith row in this case, corresponding to that. And what's the corresponding column? Well, we're in the jth column there, so we look at the jth column here. Everybody good? Everybody's happy with that? Okay, so let's write that all down. Writing down this dot product, these are those numbers, and colors. These are those numbers, and a dot product is where you multiply corresponding coordinates and add. So that's just what a dot product is. And here you go. This is altogether then sort of a coordinate point of view on the chain rule. There's a lot to say about this. First thing I'm going to say is it's pretty inefficient. First of all, look at all I had to write down. Oh my gosh. Scary looking, right? There's so many I's and J's and X's and Y's, and whoa my gosh, it's super easy to get lost in all that has to get written down here. And let's not lose sight of the fact that that's just telling you one element of this product matrix, right? If you wanted to have all of the information that the matrix form gives you, you'd have to write down a formula this ugly for each and every individual element of this matrix, and oh my god, it would take pages to write all that down. So, all right, so you can have pages and pages of intricate formulas, or you can have that. I like that. I think that's a much better way to think about it. It makes sense from the point of view of composition. It's easy to see why this is true if you understand the idea of derivative matrices as multiplicative fact. This is far superior, my humble opinion, way to deep down fundamentally to think about the chain rule. Now that said, there are circumstances where this is actually pretty handy too. Okay, but it is bulky. Okay, first thing I want to say about it, and that is don't fall for this nonsense about these partial derivatives being fractions. They are not fractions. At least they're not fractions of independently well-defined things. Because check it out, I mean, if they were, if I was allowed to just say, look at this, partial y1, oh my God, partial y1, those cancel, and oh my God, check it out, that is the same as that, and this is the same as that, and oh my gosh, look, I don't even need all of this. So it would be tempting to think everything works out if you just cancel the partial y1s. It's obvious nonsense. You can't just throw away a bunch of terms because you kind of like the intuitive, the familiar, the appeal of the familiar of this cancellation. Everybody see the problem here? Okay, so you cannot do that. It's garbage wrong. It's not close. It's not partial credit. That's nonsense. Right? Okay, so be very, very careful about that. Now, I don't get me wrong, I too used to look at this fact and think, but why not? Right? What's wrong with it really looks like I should be able to cancel there. And the answer, well, a point of view on the answer, anyway, is that this and the very similar looking that are just not the same thing. Okay, the way I like to think of these, again, I know we write them as with the exact same sort of notation. It's as if they're the same thing, but they are players of the same name in different stories. Right? So imagine you're reading some book, right? There's a character named Steve in the book. And then some totally different book by a totally different author on a totally different scenario also has a character named Steve. Yeah, they're not the same guy. Right? They're just not, right? Totally different scenarios. Well, that's what's happening here. When I say partial y1, this green partial y1 here, that's describing a particular scenario. This is a shorthand notation to represent there's a kind of a process there, and in this story, partial y1 means I'm holding all of the other y variables constant. Right? So this requires all the other y's to be constant. Okay, this partial y1 is part of a story, a different story, where xj is the thing that's being held constant. Where xj is the variable, and all of the other x's are what's being held constant. Now, let's just think this through for a moment. If I've got a bunch of x variables that are being held constant, but xj is changing, well, if xj is changing, presumably all of the y's are going to be changing. So, whoops, I wonder if this would be in red. These are completely, not only different scenarios, they are incompatible scenarios. These are different stories written by different writers, and Steve is not Steve. Everybody get it? This is very deceptive. Now, this, like a reasonable gripe to make at this point would be, well, for crying out loud, why do we write them with the same notation when they're not the same thing? That's a legitimate gripe. I'm with you. The problem is that this is how the world writes it, and I don't have the authority to influence changes in it. And I'm not even sure I know, how do I get around this problem without making the notation just bonkers bulky? And I think there's another situation where the cure is worse than the disease. I think that the best way around this is just to remember that these are not the same. These are not fractions, and you cannot cancel. You just can't do it. So anyway, that's, whether we like it or not, that's what we're left with. And heads up, don't make that mistake. Okay, let's see, how are we doing on time? Oh, we are kind of out of time here, aren't we? Yeah, let me just check. Yeah. Yeah, we're out of time. Okay, well, so be it. Drawing the line right there, and we will pick up here on, oh, wait a second, let's think this through. Monday's a holiday. Tuesday's an exam. Hard to believe, right? We've just got here. It's already exam is looming. Told you this class moves fast. Right? So anyway, I guess we will pick up here on Wednesday. All right, good luck studying for the exam. Have a great weekend. Happy, what is it, Memorial Day or something, I think? Yeah, okay, cool. Grill.
So
yes?
Is the chain rule, and that's going to be, like, everything from 2.5, is that going to be on the exam?
No, let me, let's see, let me go to the class schedule. So what we did today, okay, it's not letting me highlight, but Friday, May 23 is today, and you see that is yellow. So what I'm about to put in here, in this spot, is not fair game for exam 1. Exam 1 is just the stuff in green. Yeah. And by the way, while I'm at it, let me point out, this stuff in yellow for today, because it's not fair game for the exam, I don't really expect you to start it today, right? I expect and assume that y'all are going to be focused at this point on the material that's fair game for the exam, for crying out loud, right? So I've adjusted the date. That's why some of these dates are in red, right? So I extended the deadline for this one to give you maximum flexibility for exam studying, but nevertheless, I need to have it due before the exam because this homework is fair game for the exam and it's part of how you should be studying for the exam, right? And this one here, this stuff for Friday, I don't expect that you'll be looking at that until Tuesday after the exam. And by the way, of course, we will finish more material on Tuesday, right? So remember, you got to read these little warnings and notes in here, right? So the exam is a 50-minute exam, and then we'll do 25 minutes of lecture right after the exam, and it's weird. I know, right? But we got to do it. We're short on time. So yeah, so don't even bother. Suit yourself, of course, right? But I assume that you won't look at these homework exercises or whatever it is that we finish today until Tuesday. Yeah. Okay. All right. See y'all later. Have a good one.